Good morning, and thank you for the opportunity to present this work. The title of the presentation is A Darwinian-Type Design Methodology for Smart Structures with Digital Twin Feedback. The central idea is to reconsider structural design as a process that does not necessarily end when a structure is manufactured or deployed. Instead, a smart structure may continue to sense its environment, update its digital representation, and progressively adapt its behavior or future design state. In this presentation, I will introduce a conceptual framework that combines evolutionary design principles, smart structural systems, and digital twin feedback. The main question is simple: can smart structures evolve after deployment? In conventional engineering, most design decisions are finalized before manufacturing. Operational data are then used primarily for monitoring, maintenance, or fault detection. Here, we propose a different interpretation. Damage, load, history, and environmental exposure are treated as new evidence that can reshape the design problem itself. The digital twin, therefore, moves beyond passive monitoring. It becomes an active mechanism for updating the fitness landscape and guiding the selection of improved structural or control configurations. In this sense, structural design becomes a continuing process, one that can extend from initial conception into the service life of the structure. This shift motivates the need to move beyond static design logic. Conventional structural design is essentially an offline process. Geometry, materials, safety factors, and expected load cases are defined before the structure enters service. Once deployed, the design itself normally remains fixed, even though the actual operating conditions may differ significantly from the original assumptions. Smart structures, however, operate in environments that continuously change. They may experience unexpected loads, progressive damage, material degradation, temperature variations, or evolving mission requirements. The proposed Darwinian and digital twin approach introduces a fundamental shift. Instead of designing only once, the structure is continuously observed, its model is updated, and its performance objectives can be reconsidered. The aim is not uncontrolled change, but evidence-based and constrained adaptation throughout the structural lifecycle. The central proposition is to treat the smart structure as an evolving cyber-physical organism. This description is not biological in a literal sense. It expresses the functional coupling of three mechanisms. First, evolutionary design generates alternatives, introduces controlled variation, evaluates their performance, and retains beneficial characteristics. Second, the digital twin maintains an updated connection between the physical structure and its computational representation. Third, the smart response layer uses sensing, state estimation, and actuation to adapt the structural behavior under changing and uncertain conditions. The central hypothesis is that operational feedback can become an active design operator. In other words, the evidence collected during service can influence not only monitoring decisions, but also the future structural and control configurations. To implement this concept, we can describe a smart structure through four tightly coupled layers. The first is the structural layer, which contains the physical geometry, materials, joints, and load transfer mechanisms. This is the system whose integrity and performance must ultimately be protected. The second is the sensing layer. Distributed sensors provide information about strain, acceleration, temperature, loading conditions, and possible damage signatures. The third layer is actuation. Depending on the application, actuators may modify the shape, damping, stiffness, or internal load distribution of the structure. Finally, the intelligence layer interprets the available data. It estimates the current structural state, predicts future behavior, and supports control or redesign decisions. The essential point is that these layers cannot operate independently. Their continuous interaction transforms a conventional structure into a cyber-physical system capable of observing, interpreting, and modifying its response. The digital twin provides the mechanism that coordinates this interaction. The digital twin provides the continuous connection between the physical structure and the evolving design process. The cycle begins with observation. Sensors record the structural response together with the relevant environmental conditions. These measurements are then used to estimate quantities that cannot be observed directly, such as internal damage, stiffness degradation, or uncertain model parameters. Once synchronized with the physical system, The twin can predict future response, assess risk, and estimate the remaining performance capability of the structure. This information supports the decision stage, where fitness priorities, control settings, or candidate design modifications may be updated. Finally, the selected action may involve immediate structural control, a revised operating strategy, or a recommendation for a future redesign. We can now translate the principles of biological evolution into a controlled engineering methodology. The process begins with a population of candidate solutions. Variation is then introduced through operators such as mutation, recombination, or localized topology modification. Each candidate is evaluated using a fitness function that accounts for performance, risk, cost, resilience, and feasibility. Selection retains the solutions that provide the most valuable and robust behavior, while inheritance preserves beneficial characteristics and accumulated model knowledge for the next generation. Every candidate must satisfy explicit requirements related to stability, manufacturability, safety, actuation limits, and certification. The digital twin then provides the operational evidence needed to make this evolutionary process adaptive. This slide brings the individual concepts together into the proposed closed-loop methodology. The process begins with a population of feasible designs. Each candidate is first evaluated through physics-based simulation in order to estimate its expected response under defined operating conditions. The physical structure then provides real operational data through its sensing system. These measurements are assimilated by the digital twin, which updates the estimated structural state, model parameters, damage condition, and uncertainty. The updated twin is subsequently used to reformulate the fitness evaluation. In this way, candidate solutions are assessed not only against original design assumptions, but also against the evidence collected during operation. Selection and variation operators then generate the next design generation, and the complete cycle is repeated. We distinguish between three interconnected groups of variables. The first is the design vector, denoted by X. It may include geometric dimensions, material properties, or other parameters. The second is the physical state, represented by Z. This describes the current condition and response of the structure, including displacement, strain, or other variables. The third group contains the digital twin parameters, denoted by theta. These parameters characterize the computational model and are continuously updated using measured operational data. The digital twin links the design space, the physical state space, and the model parameter space. A critical methodological decision is to determine which variables may evolve during operation and which must remain fixed because of manufacturing, certification, or safety requirements. The fitness function is the key mechanism that translates structural objectives into evolutionary decisions. In the proposed methodology, fitness is adaptive and multi-objective. It combines performance, resilience, and feasibility. Performance may include stiffness, vibration reduction, or shape accuracy. Resilience reflects damage, tolerance, robustness, and structural redundancy. Feasibility accounts for practical constraints such as mass, actuation capability, manufacturing cost, and requirements. The relative importance of these objectives is not necessarily constant. The weighting factors may change with the mission phase, detected damage, environmental conditions, or estimated remaining life. In addition, candidates should not be ranked only according to their expected performance. Their uncertainty and associated risk must also be considered. For the digital twin to support reliable decisions, raw sensor measurements must first be converted into an actionable representation of the structural condition. At each time step, the sensing system provides measurements. Since these data contain noise and may be incomplete, a state estimator is used to reconstruct the current structural state. At the same time, model parameters are updated by comparing measured and predicted responses. The calibrated twin can then forecast the response of the structure under future loading conditions. The difference between the predicted and desired behavior produces a decision signal, which may modify the control strategy or influence the next design generation. Crucially, the twin must quantify confidence and uncertainty, because every adaptive decision depends on how reliable the estimated structural state actually is. The evolutionary update is implemented as a structured and constrained algorithm for each design generation. The process begins by generating a population of feasible candidate solutions. These candidates are evaluated through structural and control simulations under the relevant conditions. Operational measurements are then assimilated into the digital twin, allowing the structural state, model parameters, and associated uncertainties to be updated. Each candidate is subsequently scored using the adaptive fitness function. Selection retains solutions that are not only high-performing, but also robust, diverse, and feasible. The selected candidates are then modified through mutation, recombination, or other variation operators to produce the next generation. This cycle continues until convergence is achieved, a decision deadline is reached, or a safety-related trigger requires immediate action. To illustrate the methodology, consider a smart aircraft wing exposed to variable aerodynamic loads, thermal effects, and progressive local damage. Embedded sensors monitor strain, vibration, and temperature, while the digital twin updates the wing's stiffness and damage maps. Using this information, the system can reevaluate available control and structural options, redistribute loads through actuation, and recommend modifications for the next design cycle. This conceptual example shows how immediate operational adaptation and longer-term structural evolution can be integrated within one framework. To evaluate the proposed methodology, performance must be assessed across several dimensions. These include structural mass, vibration response, damage risk, energy demand, robustness, and the speed and benefit of adaptation. The objective is to determine whether successive generations improve the overall balance between structural efficiency and resilience. Any claimed benefit should also be benchmarked against static optimization, model predictive control, and non-adaptive digital twin approaches. The trends shown here are illustrative. They define the intended evaluation framework and do not represent measured results. The proposed methodology offers three main contributions. First, it extends structural design beyond deployment by using operational evidence to support continuing adaptation. Second, it introduces an uncertainty-aware evolutionary search, where candidate solutions are evaluated according to performance, risk, confidence, and changing mission priorities. Third, it transforms the digital twin from a monitoring tool into an active decision layer that updates the structural state, the fitness function, and future redesign recommendations. The framework does not replace certification. It provides a structured pathway toward evidence-based and robust adaptation. Implementation should progress through four controlled stages. The first stage is offline evolution, using high-fidelity simulations and historical operational data. The second introduces hybrid validation through hardware in-the-loop testing and controlled experiments. The third stage establishes an operational digital twin capable of online state estimation, parameter updating, and decision support. The final stage moves toward autonomous adaptation, but only where control authority and redesign actions can be safely certified. Across all stages, model credibility, data governance, real-time computing, fail-safe mechanisms, and certification evidence remain essential. To conclude, the proposed methodology moves structural engineering from design structures toward evolving structures. Darwinian operators provide a systematic mechanism for generating, evaluating, and retaining improved structural solutions. Digital twin feedback makes this evolution responsive to real operational evidence, changing conditions, and quantified uncertainty. By combining these elements with sensing and actuation, the framework creates a pathway from conventional monitoring toward resilient, adaptive, and potentially self-evolving structures. Thank you very much for your attention. I look forward to your questions and discussion.